We live in a world that's basically built on the assumption that things will work. We expect our cars to start, our bridges to hold up, our phones to connect. But we all know, sometimes from painful experience, that everything eventually fails. So why is that? What are these invisible forces that are constantly trying to tear our world apart?
Just think about that for a second. They're all incredible marvels of engineering, right? They're designed for strength, for longevity. But they share something else, something way more fundamental. And that is the key. Right from the moment they're created, every single structure we build is fighting a war on multiple fronts, a war against the forces of failure. So let's pull back the curtain and meet these invisible enemies, one by one.
Okay, first up, the enemy from within. Long before a bridge ever faces its first car or an engine its first flight, the seeds of its own destruction might already be there, planted inside the very materials it's made of.
See, no material is truly perfect. If you zoom in to a microscopic level, you're going to see all sorts of variations in the crystal structure, in the chemical makeup, even stress that gets locked into the surface during the manufacturing process. Now, these aren't really defects in the way we usually think of them. They're just part of what the material is. But any one of them, any single one, can become the starting point for a tiny crack that eventually grows into a catastrophic failure years down the line.
So, let's say you have the absolute best materials possible. You can still build failure right into the system. How? Through flaws in the design or just simple mistakes made during manufacturing. This is where human error really enters the picture.
To really get this, let's look at a concept called internal clearance. It's this tiny, often microscopic gap that's intentionally engineered between moving parts. Now you might think, hey, the tighter the fit, the better. But oh, it is way more complicated than that.
It is an incredible balancing act. If that clearance is too small, the parts rub together, they generate a ton of heat, they expand, and they can seize up completely. Game over. But if the clearance is too large, you get vibration, rattling, and the load isn't spread out evenly, which just hammers the components apart. So you see, both extremes lead directly to failure.
And clearance is just one example. You can have parts that are just slightly misaligned when they're installed, or tiny voids or cracks from the casting process, or even just imperfect welds. Every single one of these is like a little ticking time bomb, a built-in weakness, just waiting for other forces to come along and exploit it.
All right, so we've got enemies inside the material and enemies baked into the design. Now let's talk about what happens when we add the relentless attack from the outside world, the environment itself.
The environment is a powerful, powerful adversary. The single biggest attacker, by far, is corrosion. Rust and other chemical reactions that literally eat materials away. But you also have to deal with extreme heat and cold, which causes expansion and contraction, plus contamination and simple moisture, always working its way into every little crack and crevice it can find.
And here is where it gets really interesting. These forces team up. Get this, for every 1/10 of a millimeter of crack width, the rate of corrosion can jump by 15%. So a tiny manufacturing flaw isn't just a crack, it's an open door, inviting the environment to rush in and speed up the destruction.
And hey, when we talk about contamination, we're not just talking about a little bit of dust. In an industrial setting, this could be tiny, hard particles like sand or metal shavings that get into lubricants and act like liquid sandpaper, just grinding away at precision surfaces. Or it could be exposure to some seriously nasty stuff, like sour gas in the oil industry, which aggressively attacks metals.
Okay, so let's imagine we built something with perfect materials, a flawless design, and we've somehow shielded it completely from the environment. It can still fail. Why? Well, because the very act of doing its job, day in and day out, creates wear and tear.
The classic example here is metal fatigue. Think about bending a paperclip back and forth. For a while, it seems like nothing's happening, right? But on a microscopic level, a tiny crack is formed. With each and every bend, that crack grows just a little bit more, totally unseen. The metal is getting weaker and weaker until, all at once, it snaps. And this is what's so scary. A structure can seem perfectly fine right up until the exact moment of total failure.
This operational wear really comes from a few main drivers. You've got those repeated load cycles we just talked about that cause fatigue. You've got friction, which is this constant battle that we manage with lubricants. And you've got vibration and dynamic loads, all the shaking and rattling of everyday use that puts stress on every single component.
And now we get to the most important part of all this. These enemies, the inherent flaws, the design issues, the environment, and operational wear, they don't act alone. Oh no, they form this web, this chain reaction, where one type of damage creates an opening for another, leading to a cascade of failure.
Let me just walk you through how this can happen. It can all start with something incredibly small, say a slight misalignment of a bearing that's almost impossible to detect when it's brand new.
But then, you start running the machine. The vibration from normal everyday operation puts extra stress right on that misaligned part. Slowly but surely, it initiates a tiny microcrack at that stress point.
And now you've got an opening. That crack has created a pathway. It might be tiny, but it's big enough for the environment to get inside. Humidity from the air, or maybe some other moisture, starts to seep into that newly exposed metal.
And that moisture kicks off the process of corrosion, which starts eating away at the crack from the inside out, making it bigger and bigger, faster and faster. This combined attack, operational stress plus environmental corrosion, weakens the component until, finally, it breaks. A failure that seems sudden and out of nowhere was actually a slow-motion team-up of all these invisible enemies.
You know, this right here is really the core takeaway. We tend to think of failure as this single moment in time. The bridge collapses, the engine stops. But the reality is, that event is just the final visible symptom of a long, slow process of degradation that's been happening all along, completely out of sight.
So, the real question isn't just why do things break? It's more like knowing about all these invisible enemies that are aligned against everything we create. How do we get better at fighting back? How do we design, build, and maintain things that can actually withstand this constant, silent battle? That's the challenge for every single engineer out there.